Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif, and I welcome you all to the sixth video lecture on the subject of computer organization and assembly language programming. The title of today's session is Data Storage Part 1. Today we are going to change gear and will switch from the STL of combinational circuits to the topic of data representation inside computer systems. We will talk about different encodings or representations of signed and unsigned integer numbers, their ranges, storage sizes, and the concept of overflow and sign extension. At the end of the session, I will also talk about the encoding schemes used for storing characters and strings. So let us start playing. Well, this slide is just an overview of different types of numbers. We will not talk about the real, imaginary, rational, and irrational numbers today. However, just keep in mind that the irrational numbers cannot be fully and accurately represented and manipulated by the computer systems we use these days. So this is just for your information and just a review. And we move on to the concept of unsigned numbers. Uh, uh, Before moving with the unsigned numbers storage, I will like to talk about different bases as well that are used to represent these unsigned numbers as well as assigned. Well, the oldest number system is the decimal number system, having base 10. Because there are 10 different symbols used in this system, 0 to 9. And why 10? Maybe because human beings normally have 10 fingers in their hands, so the designers have just used 10 symbols for this base 10 system, called the decimal number system. Dear students, we all are very used to of using these decimal numbers and performing different arithmetic operations on them. Uh, and remember, every symbol or digit has an associate position and a weight associated with it. For example, in this example, 521 is a base 10 number. Uh, Actually, we mean 5 hundreds plus 2 tens plus 1 unit, and this sums up to 521. Well, let's talk about the binary number system having a base 2, also called the radix 2, having only two symbols, 0 and 1. Well, my dear students, the history of binary number system goes back to the 17th century when Gottfried proposed and developed the binary number system in his article named Explication di Arithmetic Binary. Well, this is a bit Latin. Anyway, more or less at the same time, Thomas Harriot, an English mathematician, also talked about the binary number system. And the details can still be found in the Harriot's manuscript in the British Museum. Well, coming out of the history, dear students, uh, this is the binary number system using which the numbers, rather, let me say that everything is finally stored inside our computer system. May it be a simple unsigned number, as shown over here, that is 1011, uh, which is actually uh, 11 in base 10. This is also positional number system. So this one has a power of a weight of 8. This 0 has a weight of 2. This one has a weight of this 0 has a weight of 4. This one has a weight of 2, and this last one has a weight of 1, 2 power 0. So this makes, or this all sums up to uh, a decimal 11. Well, even if we want to store unsigned numbers, we will be using this base 2 numbers. Or maybe it is a signed integer or a real number, or maybe a character or a string, an image or an audio note, or maybe a video clip. All these sort of data are stored inside the computer system as zeros and ones. But today, let us restrict ourselves to the representation or storage of integer numbers only inside our computer system. Dear students, there are two more common representations. Uh, the base 16 or the hexadecimal because it has 16 symbols in it, 0 to 9 and A to F, as you all might be knowing before. And this base 8 or the octal number system having 8 symbols, 0 to 7. This base 8 and base 16, these two number systems are normally used by computer system designers and programmers as they provide a human-friendly representation of these binary numbers or the binary coded values. Well, each hex digit represent uh, four binary digits, and each octal digit represent three binary digits. So we can easily convert them from uh, the binary to the base 16 or from base 16 to binary. And this table over here uh, shows the first unsigned 16 decimal number system, 0 to 15, and their hex, octal, and binary equivalent. Remember, as far as the hex are concerned, uh, hex has 16 symbols, so 0 to F. In octal, we have 7, so here we move on to two digits. And in binary, from 0 to 15, we need at least 4 bits. So the number 15 is represented in 4 digits. I expect all my students that they should be able to convert a number of any base system to any other base system before proceeding ahead. So this was about the unsigned numbers. Let's talk about the encoding of signed numbers as well. By signed number, I mean a number with a sign. Well, uh, a signed number or an integer can be positive or negative. And theoretically, there are three different ways to encode signed numbers. The first is the sign magnitude, then one's complement, and then the two's complement. Uh, if we talk about the unsigned byte range, byte means 8 bits. So in 8 bits, the smallest number is 0, and the largest number in 8 bits is all one bit that makes 255. And if we talk about the signed byte range, it ranges from -127 to +127. And in 2's complement, it is -128. And why it is that, we will see very shortly. But anyway, in case of signed numbers, we have a negative range as well as a positive range. Now the question is how we are going to store the sign. As far as the magnitude of the number is concerned, we know how to save it as we have saved the unsigned numbers. But now, along with the magnitude of the number, we want to save the sign as well, which can be 0 or 1, a positive or a negative. Okay, so first of all, let's talk about the sign magnitude way of encoding sign numbers. This is the most natural way as sign number uh, of encoding a sign number by its sign and magnitude. The most significant bit is reserved to represent or encode the sign, 0 for positive and 1 for negative, and the remaining bits represent the magnitude. If we talk about 4 bits, so this is a 4-bit representation of numbers in sign magnitude. Over here, you see the most significant bit is 0, that means this number is a positive number. So all these numbers are positive numbers. And over here, if you see, this bit is 1, so that means all these numbers are negative numbers. So if I talk about -5, so this is 1, which means negative. 101, which is the magnitude, that means 5. If I talk about +5, so it is 0, 101. So I think that makes sense. Well, we have limitations for the sign magnitude. The first limitation is there are two different encodings for zeros. We have a positive 0 and we have a negative 0. For positive 0, we have 0, 0, 0, 0 in case of 4 bits. And for negative 0, we have 1 and 0, 0, 0. So there exists a confusion whether uh, we have a positive 0 as well as we have a negative 0. Whereas in case of normal mathematics and arithmetic, we know that 0 do not have any sign associated with it. The second limitation is we cannot do subtraction by simple addition. By that I mean, if I add +2 with -3, we should get -1. But in case if I represent +2 in binary, sign magnitude like this, 0 means positive, 0, 1, 0 means 2, and -3 in binary, minus mean 1 and 3 means this. If I add these two numbers add up to something like this, which says in sign magnitude, a negative number. This one represents a negative number, and this 101 means 3. So this means -3. So the answer should not be, the answer is -5. This one is 4 and this one is 1. So answer is -5, while the answer should be -1. So that means uh, second limitation of using sign magnitude representation for negative number is that you cannot do subtraction using addition, which we are normally used to of. So the question is how to do subtraction using sign magnitude. So these are the steps. If the numbers have same sign, add magnitudes, keep the sign. If the numbers have different signs, then subtract the smaller magnitude from the larger one. The sign of the larger magnitude is the sign of the result. So this is what we are used to of while doing arithmetic from our kindergartens to onward in higher studies as well. But we need a separate hardware for subtraction in case if we want to go for this algorithm. While in most of the computers, we use just addition to do the subtraction as well. So this one sign magnitude way of encoding is not used inside our computer system. So with these limitations, we move on to another way of encoding the negative number, that is the ones complement. And it says uh, takes ones complement of the positive number to represent its corresponding negative number. So if this is 0 triple 1, we take the ones complement, so that makes 1 0 0 0, and that is 7 again, -7. So if you want to represent a number as a negative number, you just take its ones complement. This table shows the 4-bit representation of signed numbers using ones complement encoding. And whenever you see that you have 1 in the most significant bit in case of ones complement as well, so you are sure that this is a negative number, and you take its ones complement and use a negative sign with it. Ones complement has its own limitations associated with it. And the first limitation is the same as was there in the sign magnitude, and that is there are two different encoding for 0, positive and negative, as shown in this table as well. Uh, you can do the subtraction using addition. You can do the subtraction. In sign magnitude, you cannot do the subtraction using addition, but over here you can do that. However, it doesn't always work. So there are certain cases in which it will not work. For example, one of the cases, if we add a +1 with a -1, we should get 0, uh, but actually we get a -0. So if you convert a +1 in ones complement, and if you represent a -1 in ones complement, and if you add them up, you get this, all ones, 4 ones. So if over here you see 4 ones means -0. So this is again a limitation. So finally, we move on to the third and the final way of representing uh, signed numbers, and that is 2's complement. And it is again very simple. It says take 2's complement of the positive number to represent its corresponding negative number. So if this is +7, which says 0, 1, 1, 1, so you need to take its 2's complement now, which is 1, 0, 0, 1. 1 0 0 1 1 0 0 1, which makes it -7. So whenever you want to represent a number with a negative sign, you take its 2's complement. The 4-bit representation, all shown over here. Please do practice that. And whenever a sign number has MSB, most significant bit as 1, that means this is a negative number. So if you want to know what this number is, you take its 2's complement and represent it with a negative sign. So this is 1 1 0 1. You take the 2's complement, which says 1 1 0 0, which is 3. You represent it with a negative sign, which becomes -3. Okay. So all these limitations which we have talked about in the previous slides are resolved in two's complement. First of all, there is single encoding for zero. There is no concept of negative zero in two's complement. So whether it is a plus zero, it is a minus zero, we represent it with like this. You take its two's complement, it is all zeros, and the positive zero is also represented the same way. So since we have one representation for the positive and the negative zero, so that's why we have another additional uh, value available on the negative side, and that is minus 8. So you can see that in 2's complement, we have an additional value minus 8 over here, while in sign magnitude and 1's complement, the range was from plus 7 to minus 7 in 4 bits. Moreover, subtraction can be done using addition, so you don't need a separate hardware for that. And this plus 1 and minus 1, if added, of course, results 0. We have seen this exception in case of 1's complement. It doesn't anymore exist in 2's complement. And similarly, if this is a plus 2, so in 4 bits it is 0010, and to represent a minus 3, you see this is 1101, 1101. You add them up and you get all ones, and all ones is minus 1 and minus 1. The result works fine. However, if I add 7 plus 1, so it becomes minus 8. So this is plus 7, this is plus 1, and once I add them up, I get this value in 4 bits. And if I check out the binary bits, it represents minus 8, while the answer should be plus 8. So this concept is known as overflow. I will talk about it a bit later. Uh, a bit later. So I think you have a fair idea now about the unsigned representation of numbers, integer numbers, the signed representation, in which we have seen three ways: the sign magnitude, one's complement, and two's complement. And the best, apparently best one is the two's complement. Okay. Mm, dear students, let me build a scenario for you for complete understanding. Suppose I ask you that there is a 4-bit binary number stored inside the computer, and that is 1101. This one, okay, 1101. And I ask you, what is this number in base 10? So now you cannot answer this question so easily. You will ask me, first tell me, is it unsigned or signed? Okay, I tell you that it is unsigned. You will very quickly tell me that if this number 1101 is unsigned, so this is 8 plus 4 plus 0 plus 1, this is 13. So you will come out to 13. This is 13 in base 10. So that is good. What if I tell you that this 1101 is a signed number? Tell me what it is in binary. Once again, you cannot answer this question until I tell you about the encoding scheme that is used to store this signed number. Well, if I tell you that the encoding scheme is sign magnitude, so you will say fine. The most significant bit is 1, so it is a negative number, and the remaining three bits are 101. That means 5. So this is minus 5. So in sign magnitude, this is minus 5. Similarly, if I tell you that this 1101 is a signed number, and the encoding scheme used to represent this number, this 1101, is one's complement, and then you will say, so fine, since the most significant bit is 1, so this is a negative number, and I need to take the ones complement of this number, which comes out to be, of course, 0, 1, 0, and 0, 1, 0 means 2. So you will attach a negative sign with it, and you say the answer is minus 2. So here it is, minus 2. And you can repeat the similar procedure in case if this number is encoded using 2's complement. So my dear students, this 1101 may mean 13, -2, -5, or -3. In decimal, depending on whether it is an unsigned or signed number, then what is the exact encoding scheme of each. Uh, so to avoid this confusion and for the reasons mentioned on previous slides, almost all computer systems as well as the internet use 2's complement to represent signed numbers. So in future, we will just be talking about if we are talking about unsigned representation, so there is only one technique, and if we will be talking about the signed number representation of numbers, so we will be using 2's complement to represent signed numbers and to store signed numbers inside our computer system. Okay, well, this slide shows a mapping between the 4-bit unsigned numbers and the signed numbers using 2's complement representation. From the 0 to 7, you can see that the mapping is same, and for the rest of the 4-bit numbers, you can subtract or add 16 to move from unsigned to signed or to move from signed to unsigned, respectively. Okay, well, the minimum and maximum number that can be stored in a given number of bits also depends on the encoding scheme used. So this slide shows you the formula to calculate the range for unsigned as well as signed numbers, where n represent the storage size in bits. Please stop the video over here and confirm using different values of n starting from 4 as shown in this table, and have a very clear understanding about the range of the unsigned and the signed numbers that can be stored inside a particular storage size: 4 bits, 8 bits, 16 bits, and so on. Okay, so this slide shows the ranges for unsigned and signed numbers using 2's complement representation for different storage sizes. You can note for the signed ranges, there is one extra negative number. For the signed ranges, you have one extra negative number over this side, since there is uh, no encoding for -0, and in 2's complement, we have an additional negative number that exists inside the range. Well, using 64-bit, well, over here, uh, we can store quite a large number. However, it may not be able to store the factorial of 20. Well, there do exist a solution, and we will talk about it in the next lecture, inshallah. Okay, so we are done with this. Now I'm going to talk about the concept of overflow. Then using the unsigned numbers, or maybe using the 2's complement. And here is a slide in which I have shown you our table over here, which represents the 16 decimal numbers and their corresponding 4-bit binary numbers. Well, dear students, overflow is a condition that occurs when a calculation produces a result that is greater in magnitude than what a given register or storage location can store. And an overflow can be detected by the hardware if there is a carryout from the most significant bit after addition. And remember, uh, this way we can detect the overflow after unsigned addition. If there are two unsigned numbers, we add them and there is a carry out from the most significant bit, we say that uh, the result is an overflow. The result is incorrect now. So there is a carry flag inside almost all systems that are used to confirm this overflow. Let us say that to keep things simple, we talk about 4-bit unsigned numbers. And let's suppose there is a number this 9 in binary and this 5 in binary. We add these two numbers, we get 14. And this 110 and 1 over here, and this is 14 in binary. So is this an overflow? Of course, this is not an overflow. You can see that this 1110, this 1110 is 14 over here. So this is not overflow. Let me take another case. We have the number 10 over here and the number 7 over here. 10 plus 7 is 17. And this is the binary of 10. This is the binary of 7. Of course, unsigned. Once we add them up, we have a carry out from this most significant bit, which is placed over here. So the container was of 4 bits. Now the answer is coming in 5 bits, and that is of course not correct. So the answer is now 1. In 4 bits, the answer is 1. Whether we know that the answer should be 17. So we say that an overflow has occurred. Okay, so this was a case mm, for overflow in case of unsigned numbers. Let's see the case of overflow in case of signed numbers as well. Now over here, you can see this table, the 4-bit binary numbers. The range is from -8 to +7, whose complement representation, the negative numbers as well as the positive numbers. Well, overflow will never occur when you add a positive number to a negative number. It will occur only when the two operands have same sign, but the result hasn't. Well, this is quite simple. Read it again. When you add a positive number with a negative numbers, overflow will never occur. And this is quite natural. It will occur only when you will be adding two positive numbers or two negative numbers. And you can detect that if you add two positive numbers and the result is negative, you say that an overflow has occurred, and vice versa. Okay, so overflow will occur when you add two negative numbers and get a positive result. This is called negative overflow, and this is the example of it. You see, this is -6, this is -7. When these two are added, you get the result in these 4 bits, which is positive. So you say that an overflow has occurred. Similarly, overflow will occur when you add two positive numbers and get a negative result. This is called positive overflow. Let's suppose we have added 6 with 5, and this is 6, this is 5. We get 1011, and of course, this is a negative number because this bit is 1. So after adding two positive numbers, how can we get a negative number? So this is again an overflow. Please do practice these on on different numbers, and uh, the question is this an overflow? So this is a number, I don't know what it is. This is another number, I don't know what it is. I'm adding it, and there is a carry out from the most significant bit. So we have a carry out over here. So it appears that if there is a carry out from the most significant bit, it should be an overflow. But I think this is not an overflow. So all ones means -1, and this 1110 means -2. -1 and -2, we add them, we get -3. And you see 3 minus 3 is 1101, and this is 1101. So this is not an overflow, because even after truncating this fifth bit, that is the carry out, and the result, getting the result in 4 bits, the result is correct. So the $100 question is, when adding two signed numbers, how to detect that an overflow has occurred? Well, before I give you the answer of this question, remember, dear students, there is a concept of sign extension. By sign extension, I mean by increasing the number of bits of a binary number while preserving its sign and magnitude. Uh, this can be done by padding the left side with sign bits. So, in simple words, if I place lot of zeros on the left of this +7, this will remain 7. Let me repeat again. By adding lot of zeros on the left of this +5, 0, 1, 0, 1, this will remain 0, 0, 0, 0, 0, 1, 0, 1. So adding zeros on the left is the concept of sign extension. Similarly, if I come up over here, if I add lot of ones on this left side of this -7, it will remain -7. So in case of positive numbers, if you add zeros on the left, in case of negative numbers, if you add ones on the left, this is called sign extension. It doesn't have any impact on the magnitude of the number. And now let me move ahead and let me answer the question as how we can detect the overflow. Okay, this can be detected by the hardware if there is a carryout from the most significant bit. In case of unsigned numbers, we have seen that. But now we are more interested how to detect the overflow when we are going to add two signed numbers. This can be detected by the hardware if there is a carry in the MSP and carry out from the MSP are different. Let me repeat again. In case of signed numbers, an overflow will occur if the carry in the MSP and the carry out of the MSP are different. In case of unsigned number, the hardware normally keeps a flag that is called carry flag, and it checks the carry flag. If the carry flag is set, it says overflow has occurred. In case of signed numbers, the hardware keeps an overflow flag, the OF flag. So after addition, if the OF flag is set, it says an overflow has occurred. And how the overflow flag is set, that is very simple. Uh, we XOR the carry in the MSP and the carry out bit of the MSP. We XOR them and place them in the overflow flag. Okay, so this is an example of 4-bit signed numbers in 2's complement representation. And any one of you can tell me, is this an overflow or not? Well, without going into the calculation, you can say that since the carry inside the MSP and the carry out of the MSP both are 1, so this is not an overflow. So if you see, this is -1 in 2's complement, this is -2 in 2's complement, and this is -3 in 2's complement, which is absolutely correct. Please do the working. Please do the math at your own time. And in case if we talk about this is of course an overflow because the carry inside the MSP is 0 and the carry out is 1. They both are different, so overflow has occurred. This is a -6 in 2's complement, and this is a -7 in 2's complement. And of course, this is if I take the 2's complement of this number, this becomes 1011, which is -13. So this is an overflow. Similarly, please do check these other examples as well. I have a very clear concept of the overflow in case of signed numbers. And let me move ahead. So I think that is enough for the unsigned and the signed integer number representations inside the computer system. And before closing today's session, let us also see how characters are represented or encoded inside our computer systems. The ASCII American Standard Code for Information Interchange. This is a code used to give each symbol or key from the keyboard a unique number called the ASCII code. Uh, it can be used to convert text into ASCII code and then into binary code. So the standard ASCII is 7-bit, having 128 different combinations, and the extended ASCII is of 8 bits. These are some of the commonly used ASCII characters. The small a has an ASCII character of 97 and it moves ahead. The capital A has a representation of 65 or encoding of 65 and it moves ahead. And between the lower and the uppercase character, you can observe a difference of 32, I think. So if I add 32 in capital A, I get 97. So to convert a uppercase character to lowercase, I add 32 to it, and to do the vice versa, I can subtract 32. Similarly, these are the ASCII code for the digits 0 to 9, 48, 49, 50, and so on. And these are the some special characters as well. Anyway, dear students, today the Unicode standard is a universal character encoding standard used for representation of text for computer processing. Unlike 7-bit standard ASCII, which can encode English language alphabets only, Unicode can encode a variety of languages spoken around the world. The Unicode is a standard scheme for representing plain text. However, it is not a scheme for representing rich text. Unicode is platform, program, and language independent. And the common encoding formats used by Unicode are UTF-8, UTF-16, and UTF-32. By UTF, I means Unicode Transformation Format. UTF-8 is default encoding form for a variety of internet standards and uses one byte. And the first 128 Unicode points represent the ASCII characters, which means that any ASCII text is also a UTF-8 text. This is important. Well, the WTC, that is World Wide Web Consortium, specifies that all XML processors must read UTF-8 and UTF-16 encoding. Anyway, so dear students, that is all for today's session, and these are the tasks you need to do. I want you to practice converting signed and unsigned numbers from one base to another base. For example, decimal, binary, octal, and hex. And once you have done that and you want to confirm your working, you can use these online base conversion calculators. The links are given. I also want you to write down a C program that checks the minimum and maximum value that can be stored in signed or unsigned data types like the char data type, short, int, long, and long data type. And does this has something to do with the hardware and operating system? And you need to confirm if you are working on a 32-bit hardware and 32-bit operating system, what are the results? And if you are working on a 64-bit hardware and a 64-bit operating system, then what are the results? Uh, well, I also want you to write down a C program that verify as what happens when a signed or unsigned variable of char data type overflows, or rather any data type overflows. Well, in the end, I will say that coming to office hours does not mean you are academically weak, and I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.